there will be reflection light. If we keep increasing the angles, what we will see? We will see the total internal reflection light. This is the basic. But if we put another metal film on the surface, there will be another because on the surface of the metal, we have a lot of free charges, right? We have free electrons, and the light itself is electromechanical. It's actually an energy, right? It's a electromagnetic waves. So with the introduction of the electromagnetic waves, the free electrons, they will oscillate. When this oscillation wavelengths match with the wave vector through the surface of the metal, there will be the resonance condition. And from this equation, we can see here, it is related to the angle. At a certain angle, you will see when the resonance occurs, how the reflection light will be absorbed by the electrons. So we will see a very sharp dip here. As we see, this is right one. We have a dip. This is called SPRD or SPR angle. So as its angle, all the energies are on the surface of the gold film or the silver film. So it gives us a very high sensitive surface. So among all these concepts I just mentioned, there are two words I want you to understand. One is nascent wave, which is actually when the total internal reflection occurs, there a part of energy is trapped at the surface of the metal. That one is called evanescent wave. And also another concept is the surface plasma, which is actually the activated electrons on the surface. So this is a very important two concepts involved in the SPR excitation. So with this process, we have already understand, right? So we can see here is a video. May give you a better description of this process. You see there is a evanescent energy waves, right? So when it occurs, there will be a dip in the reflection intensities. Okay? So this is SPR. And SPR, the reason we want to work with SPR is basically it's really sensitive to the boundary conditions. All the refractive index change, all the electron changes can give us signals. And also it's a very universal signal, so we don't need any labeling. So we can do the real-time label-free detection. And with this real-time detection, we can not only detect the concentration of the analytes, we can also monitor the genetics. It is especially important for some drug screenings because when we are ranking the drugs, we want to know how fast the drug can bind with targets and how long it can stay with the target, right? We have to evaluate the efficacy of the drugs. And also, it's actually a very good technology to be combined with other methods like the electrochemistry. So when we combine the bioreceptor elements with SPR, we can obtain both a very specific and also very sensitive techniques for the detection. Since SPR is one of my work, so I will go directly to some of my work here. So my basic work here and my research focus is actually we're trying to build some label-free techniques and also some optical instrumentation. We are trying to solve the clinical issues. So there are two different directions here. So first one, we are trying to solve the precision medicine. We are trying to screen the targeted drugs, target as the cell surface receptors. So another direction I'm working on is we are targeting as current susceptibility, I mean the antimicrobial resistant problems. We are trying to build a point here, imaging instruments to to enable the direct AST detection. We want to reduce the current very long period of susceptibility detection time to about 2 to 3 hours. So today I will make first focus on the plasmonic imaging directions. So you can see here what we do to improve this technology is we replace the photo detector with CCD cameras. So when we change it with the camera, we will see what we can see resolve the spatial information. We can see some local changes, as you can see from these two videos. So we can enable the high throughput imaging, and also we can see at the subspatial locations of a single cell how the molecular reaction, how the binding occurs. And furthermore, when we're trying to further improve our spatial resolution in both X and Y, and we replace the prism with high numerical aperture objectives, which can allow us to give a high angle investigation. So with this setup, we can resolve very small particles. Here, as we show here, we can resolve like 100, less than 100 silicon particles, which is actually already smaller than the refraction limit. Right? This is because SPR is very sensitive, so the very small particles can be resolved. Also, with the imaging of single cells, we can obtain not only the shape of itself, we can see the 3D structures. We will know which part is more closer to the surface, which part is away from the surface. So it gives us another view of the cell, what the optical, like the bright field microscope cannot provide. Also, because SPR is very sensitive to both the charges and the refractive index, so we integrate the electrical detection together. And with this one, we can further improve the capability of our methods. We can use the transmitted image to show the morphology of the signals, and use SPR to show the dynamic molecular interactions. And for the impedance ones, you can see how the cell is impacted, how it's already broken with chemical and impedance signals here. So with this method, we have already achieved single molecule, single cell imaging. We can do single proteins interaction to the surface, and also we can see single cells, like a signal transduction. We already see the action potential in the neuron cells, how it propagates along the single axis. And today I will introduce one typical applications we have been using with our SPR microscope, which is the molecular detection on the cell surface. Why we are very particular interested in this process? Because the receptor on the cell surface is very important. It is the start of a lot of cell recognition and communication processes. Also, more importantly, it is the target of the current drugs. So you can see from here, it's already been established more than 60% of the drug is memory proteins. But currently, when we are trying to develop, we are trying to screening drugs target as this receptor. What we have to do is we have to express the target on the cells. Then we have to isolate it and purify it, which is a very laborious process. And also, sometimes when we get the memory protein out, it will lose its function, lose its structure. So there is a very specific needed. We want to develop in suiting a very native methods by trying to capture the native detection on the cell surface. Yeah, this is another summary of the of the motivation, the significance that why we are doing the molecular interaction on the surface, because we want to understand the cellular function, the signal process, and also we want to discover drugs, right? So the current challenge is the membrane protein is really hard to measure because it's very hard to prove as they are in this membrane surface. And currently, the membrane protein is called on druggable targets. So a lot of studies have been focused on developing methods to purify it. So what we have done is we just combine the cell culture with our SPR imaging systems. So you can see from here, we can see the bright field to see the morphology of cells, and also we can see how the cell interact with the surface. And when we introduce the drug targets on the surface, we will see the real-time binding, both the temporal responses, right, and the spatial distribution result. So currently, we're trying to establish this method with a very typical receptor, which is the oncogene called EGFR, which it has been demonstrated related with the development of the cancers. So we use another cell, which is the A431 cells. They are overexpressed with EGFR receptor. So we're trying to screen an antibody drug which can block this target, which will stop the ever growing the keep growing of the cells. We are trying to stop the growing to cure the cancer development. So you can see from our signals, we can see very obvious binding signals here, which indicate the antibody drug really binds to targets it binds. And also from the binding curve, we can get the kinetics, which is associated rate. It tells us how fast the drug reacts with it. And also we get the dissociated rate constant. It tells us how long it can stay with the receptor. So with these two values, it's very easy to rank drugs. So with this method, actually we collaborate with pharmaceutical companies. We're trying to provide some data and some values for their drug screening. And also, based on the kinetics between the drug targets and the drug molecules, we see very diverse binding kinetics. So we thought it should be related with some mechanisms. So you can see from here, we test the binding kinetics between the resistant cells and some sensitive cells. Because in the clinic, when we use this drug for a long time, some patients will stop responding to it. That means it develops resistance to these drugs. But the mechanism is not very clear. From our result, we can see for the resistant patients, the drug seems to band and drop. It's very fast. We call it non-specific banding. It's very likely because the banding pocket has been blocked by other molecules. So with our results of the banding curves, we can hypothesize the resistant mechanisms. So there may be two different ways of the resistant development. One is called the high-pass hypothesis. So if the banding curve is still very beautiful banding, but the patient is not responding to the therapy, it means it goes through the high-pass hypothesis. They develop another new signaling ways to activate the growth of the cells. But if the banding is like go very fast and then drop out, it causes another alternative hypothesis. It means the banding pocket has been blocked. So that's why we can use our kinetics to screening the drugs and also to explain why the patient is resistant to certain drugs. And also, as we mentioned, SPR is a mass sensitive method. So we can transmit the response, the signal response to the nice density we obtained. So what we can do is we can quantify the receptor expression levels on single cell. This is very important because we know EGFR is a cancer biomarker, right? If we can quantify the exact expression levels, we can use it to evaluate the status of the disease, and also we can use it to evaluate how the treatment is working, right? So it also provide us a good way for the tumor cell infections. So based on this capacity, we develop another application. We are trying to modify profiling the glycoproteins on the single cells because glycans are very important. From this one, we can see it's a Nobel Prize in 2023. They are given to the scientists who developed the click chemistry to labeling the glycans on cell surface, because glycans are very diverse structures and very hard. So what we can do is we are trying to solve this problem, not with labeling, but with specific genetic modifications. We can quantify the real-time binding terms and to recognize different bindings and recognize different glycans. So based on this proposal, we already achieved the detection of multiple glycans with a little bit less the molecules. We use lectins here. So we quantify the glycans as lectin kinetics, and we can see for the tumor cells, we test the normal cells and the pre-cancer cells and the tumor cells and the the metastasis tumor cells. And we observe very different patterns of the glycan expression. Right. So with this method, we can give us another choice, not the best method, but another choice. We can use less targets, use less probes, and without labeling, we can mapping the distribution of the glycans on the cell surface, and for the cancer cell detection, and for the cancer status validation. Okay, so another application we are trying to do now is we are trying to see how the cancer development will affect the cell and the surface interactions. So what we do is we're trying to quantify real-time process of surface and substrate interaction. Also, we are trying to measure the movement and macromotions when the cell attached to the cell, which is related to the linkers. To the cells from this cartoon here, we have to know it's not like they are lying down on the surface. They are actually linkers. They have a lot of linkers. They tether the cells to the surface, and the number of the tethers and the strings spring constant of the linkers is related with how much the cell is tethered to the surface. So what we can quantify is we quantify the tether numbers, we quantify the tether strings. With this method, what we observe is for the primary tumor cells, sometimes it attaches those cells to the surface more closely and more faster. But for the metastatic tumor cells, it's very hard for them to attach to the surface, and also it's very loose. I didn't show the videos here, but you can imagine it's like away from the surface and move a lot. So a very weak. It's a very weak landing with the metastatic tumors. So with this method, we can do the study of the tumor progression distinguishing, right? So this is another application we are trying to do. For this slide, this is the video. So it's similar. It's still the surface and the cell interactions. You can see when we give another external stimulation, mechanical stimulation, you can see very fast responding of the cells. And you can observe like holes over there is actually the cell, some part of the cells away from the surface. So for our methods is that we can really see a different view of the cells, how it interacts with surface or with other molecules, which this kind of information is very hard to be achieved with traditional optical imaging systems. Okay. Oh, okay. Yeah. Okay. So this one is very interesting. Just because of time limit, I'm just going to quickly introduce. This is we are trying to use our SPR microscopy to image the intracellular organelles. This organelles is actually mitochondria. You can see this is how mitochondria is moving along the cytoskeleton. See. Yeah, this is actually the very interesting. It tells us that all the organelles inside the cells are not moving very randomly. It all trafficking through the actions, right? So this is another work we have working on. A little bit summary. I cannot go through all the examples here. So basically, with very high sensitivity of our SPR imaging and the microscopy systems, we can see all the local interactions of the cells, including the extracellular interactions, also the intracellular mitochondria, right? So we also have done some functional imaging. We're trying to resolve the single action potentials along the neurons. So the image left here, you can see is cortex primary neurons. We can see the structure of neurons. Yeah, I forgot to put a video here. Actually, we can see how the action potential is trafficking or propagation along the axis. It's also very interesting. If you guys want to know more, you can check with the papers. We have papers already published on this part. Okay. Okay. This one is actually another. I will give you a brief summary of another work I have been working on. It's actually the direct antimicrobial susceptibility testing. Like I mentioned, we are trying to solve the question, the threat of the resistant problems. So we built a very sensitive single cell scattering. You can see here all those blinking ones are single bacterial cells, like the blinking stars at night. So the basic principle is that we are trying to build a dark field imaging. We remove the background intensities of the light. Then we can see the single bacteria. With this method, we can allow for the identification of single bacteria from the raw blood samples. We also try the urine samples. And what we have achieved is that we can do the susceptibility testing within like 2 to 3 hours, which has been like over 3 days with the method. So this is another work. We are recently working on this manuscript has already been submitted for revision right now. I think that's basically what I want to cover about some of my work. And the next I'm going to go through is Professor Liu's research. So Professor Liu is mainly working on the people and the wearable sensing systems. So the problem he's trying to solve is the continuous monitoring of the signals. And the methods he was trying to use is electrochemical sensing, because the easy method is more easy for us to make it small, so it's more compatible with wearable systems. So you can see the motivation. Okay, the motivation why we want to do the monitoring, why we want to do the wearable devices. It's basically because in the current medical care, what we detect is actually just 1 point vitals, right? So it provides very limited values. And sometimes it gives us very maybe false positive or false negative results. Due to this problem, so we have these point-of-care solutions. We have a portable sensors here, but we can achieve multiple points. Still, it's very hard for the patient to follow the detection all the time. And also, it gives us very limited prediction data for the diagnosis, right? A better solution we are trying to achieve is wearable biosensors. We want to get the continuous monitoring and also the real-time to predict the disease propagation. So this is basically the motivation for these studies. And currently we have a lot of smartphones, smart rings, right? We are trying to monitor the body temperature, oxygen, and the pulse. But when we come to the biochemical sensing, there are very limited products here, right? But people are trying to propose. We are to propose if we have a biochemical sensing smartwatch, that would be very meaningful because it can help us monitor all the metabolics inside our bodies from the sweat or from the saliva, from the urine. It can give us a very comprehensive information about our body. So this is a basic fundamental introduction to wearable devices. And yeah, due to time limit, I will go faster. Okay. So what Professor Liu is trying to solve is actually we want to get rid of the battery. This battery is very kind of like bulky and can be you need to recharge it very frequently. So it's not very optimal solution for the wearable devices. So one solution we use is onboard batteries, which is a near field communication, the NFC. We all know we use NFC to purchase, right? We use NFC to communicate right now with our cell phones. So based on this cell phone-based NFC, they develop a lot of cell phone-based devices here. So this example is a battery-free and wireless electrical system for the sweat. They can continuously monitor the glucose and also the ions. This is to show how the real-time you can see. So when you are doing some exercise, your sweat will be monitored to see how the ions is reducing or increasing. Okay. And also, apart from the ions, based on immunosensors, they also achieve the detection of the pulse, which is a very important biomarker for the evaluate of the stress levels. You can see here, this is we saw very obvious patterns in the morning and in the evening. The cortisol levels are affected. Also, apart from the monitoring, we are also trying to close this loop from monitoring to post-treatment. So what we did is we developed a smart dressing. With this dressing, we can monitor the vitals, such as the temperature, pH, and also the uric acid. We are trying to describe the infection status. And if it's still in the infectious condition, we will use the electrical controlled release of the drugs. You can see the drug molecules can be released as necessary. So with this method, we can achieve not just monitoring, but also treatment. Yeah, This is we published on AFM. And another very recent work we are trying to do is we are trying to get rid of the cell phone already. We are trying to working on the self-powered systems. The self-powered technologies we use here is TEG methods. We are trying to harvest the body heat. So with the body heat, we can transform the heat into the electric signals and use it to power our sensors. So with this method, we have achieved the real-time tracking and monitoring of a variety of indicators, including the heart rate, the ions, and also the velocity. So it gives us another way of our management. This is when we integrate the gas sensors with this self-powered system, we achieve the monitoring. Okay. This is some other applications we have been working on by using these wearable devices to monitor the food, for the environment monitoring, and also for the breath monitoring. Okay. I think the time is already. Okay. So you guys have any questions?
Yeah, thank you, Prof. Zhang, for the presentation. And now we will proceed to the Q&A session.
Okay.
Any student would like to ask the question can type in the chat box or unmute yourself.
Any questions?
Yeah, it's very hard to communicate like this.
You guys can type or ask anything. You guys want to ask question can go to front using the laptop microphone or using your guys login one.去问，赶紧去问，真的，这个人是一个教授哎，很年轻吧，33岁不到哎，快去认识一下，去前面问，快去，你这边可以开吗？啊，你看问题，啊，你问问题。你要问吗
？I didn't see anything here, so.
Wait,快点。
Right.
What the fuck?
Okay, someone just okay.
Yeah, Prof, we have a question from here. No, you just.
Oh, 聊天对。
Sorry, I cannot hear. Can you maybe type it?
Yeah, his question is EGFR receptor.
Sorry, the EGFR receptor what?
Yeah, what's the meaning of that?
Oh, what's the meaning? Oh, okay.
Yeah.
The epidermal growth factor receptors. It can react with the growth factor. Does that make sense? So when the growth factor will react to the receptor on the cell surface, it will stimulate the cell to continuously growth and to become a cancer cell. So that's why it's an oncogene, and a lot of cancer cells overexpress with this receptor. Does that make sense?
Yes, this answer already answered his question. And